Okay. So we had talked about how models are thinking tools. Models serve as thinking tools. They help us think through the consequences of our assumptions, because sometimes, our assumptions about the world dynamically, how things work out there, the processes in the world, they lead to dynamic consequences that are not obvious. With these models we're working with, maybe we'll have some vague idea of how they might behave if we just ran them, but until we really run them with particular parameters, we might fool ourselves. And understanding dynamic consequences, we can often compare with real world data. And often we try to make sense of data from the world by this phase here. But another use of models is just connecting up an understanding of how our assumptions ripple through to dynamic consequences, sharpening our thinking about this area. And unfortunately, each of these pens is successively problematic. This is really quite extraordinary. I'm going to be painting in pastels. Okay, so let's try this. This is kind of stylized models. Stylized models are going to fit in to help us think through the links between our assumptions and the dynamic consequences. How certain features of a situation might lead to certain consequences. And we saw that last time with one model. What was that model that was very stylized? It wasn't an attempt to model in all details what was going on out there in the world, but it was instead a fairly stylized model. What was that we saw last time? It was called the Game of Life, yeah. And that Game of Life was, by any description, a quite poor approximation to processes out there in the world in terms of its detailed formulation. It didn't try to replicate, the details of how DNA is represented in an organism, how sexual and asexual reproduction happen, how mitosis, occurs. It didn't try to replicate, the membrane of the cell and all of its details. Instead, it was a very simple, high-level characterization of rules of evolution of an agent, and it captured a few essentials. The term I like to use from this, borrowing from my colleague Carl Simon at Michigan, is he talks about caricature models. These are models that they're like caricatures in a political cartoon. They bring out a big feature, like a big chin or a big nose of someone, and it captures sort of an essential feature of the situation without capturing all the realistic details. It captures something of central focus. And here, with these stylized models, we capture a few essentials. So that model last time, the Game of Life, what did it capture? So anyone remember? We could go load it in if we want to. Some of you may have it loaded yet in your projects here. Here's the Game of Life. What did this model capture in terms of some of its bigger features? What processes? What things were going on in this model?
The cells were changing colors.
Okay, yeah, and okay, so cells lived and died based on their proximity to other cells. So it captured the fact that in the world, when we're dealing with cellular life forms, there's probably some dependence of one cell on another. They're independent. They're not totally independent of each other. And there's some process of colonization, right, whereby a patch that was previously empty might be colonized, might be filled in by a neighboring cell that's already living. And it captured the fact that these cells can live and die based on their conditions. In this case, it's a very simplistic representation, but it's one that they captured those features of the situation. We saw that last time this sort of simulation is pretty specific. The outcomes of it are pretty specific to our assumptions. And I noted how you could kind of play around with it by clicking at places here, and you could set off whole chains of events by artfully placed clicks. if we change those rules ever so slightly, we change the rules so that instead of a cell being able to survive, say, with 4 neighbors, or between 2 and 3 neighbors it's able to survive, we could allow it to survive up to 4 neighbors. I went to cell, and I went on step, and I changed that number there. And by running it here, do you think we'll see something very similar or different? In fact, it's rather different. It's different in a way that you wouldn't think would be the case, right? It's not obvious. Why is it that somehow going from 3 to 4 leads it from this kind of state of having fairly disconnected regions that are evolving quickly to a fairly ordered state? And you might note that as you sort of click in here, there's sometimes some global rearrangements that can be caused by sort of small clicks. So small changes in the rules can make big difference in the outcomes. And we saw, in fact, the last time that a formulation was computationally universal, meaning you could perform any computation that could be described on a modern-day computer, you could characterize in the game of life. And I may have you play around a little bit more with this, but this is a stylized model. It helps stimulating high-level insight about how to go from a model description and the assumptions to the dynamic consequences. So that's great. It abstracts away from all the details of particular situations, and it lets you focus on a few essentials. Okay. Now, a key component of this was spatial embedding. We had agents situated in space. In this case, the space was discrete. We had these small patches here, these individual patches into which agents were placed. And those agents' behavior was dependent on their neighbors in the patches. And I talked about 3 environments that we'll be seeing at one level or another. Continuous embedding, we'll be seeing that more today. Discrete cells, we saw some of that, and we'll explore it a little bit more today. And GIS, where we're actually putting them in a geographical space, something I may ask you to review in a separate take-home exercise. We saw the anti-logic environment could be used to realize these things. Okay. Okay. So the game of life is one of the most famous, what's called cellular automaton. It involves discrete time. It goes and time advances in lockstep. All agents are updated at once. They depend for their update to the next time step on the current state. But all those updates occur at once. And they occur at a discrete set of ticks. In other words, instead of being defined over in a continuous way, as in system dynamics, it goes through discrete time points, time chunks, time 1, time 2, time 3, time 4. I know you like to know what happens when I get to time 100. And I won't face the wall. The point here is that it's not continuous time, it's discrete time. System dynamics, I would note, has very similar at a certain level. The flows depend for their values on the current what? Current state of the system, right? The flows are defined in terms of the stocks in system dynamics, are they not? Yeah, so you have a stock, you have a flow out. Here's our first order delay. Alpha, this is x, this is alpha x. The change, as represented by the flow, the rate of change of the state is given by alpha x here, and the current state is x. So once again, the change is based on the current state, right? We see that here with the game of life. Whether a cell lives or dies depends on the current state of the system, whether it's currently alive or dead, and whether there's a certain number and what number of cells are around it. So the change, again, depends on the current state. In system dynamics, the flow, which represents the change, depends on the current state. In agent-based modeling, where we had state charts like this, the change, whether or not you go down here, maybe this is associated with a rate transition, or maybe this is associated with a timeout transition from one to the other. That change, whether or not this change occurs, depends on the current state of the model. Whether this agent is in this state right now, and for how long they've been in that state. That's part of the current state, ladies and gentlemen, of the model. So system dynamics, agent-based modeling. Cellular Automata is an example of agent-based modeling. The change depends on the current state of the system. And everything here updates in lockstep, just as in system dynamics. All the flows are computed, and behind the scenes, the states are all updated in lockstep. Okay? So here we have a certain commonality between these, but in system dynamics, we have continuous time. At least it's a continuous time approximation. We're simulating it as if this is a continuous time process. And hence, we don't get jumps to jumps. We get a sort of a nice smooth decrease in x of t over time as sort of e to the minus alpha t. Continuous time. Time is simulated on a continuous basis, not in discrete steps. In cellular automata, they're traditionally simulated in discrete ticks. And indeed, that's very common for many agent-based models. So here, cells are viewed as surrounded by 4 neighbors. And living cells require some neighboring space, also some proximity to living cells. A cell is colonized if it has an ideal nurturing environment, 3 surrounding cells, and it dies if it's too crowded or too isolated. And there's no mobility. I want to draw attention to this, because next we're going to go to a case of mobility. Okay, so I covered this in a little bit more detail, how this is realized. Note that you can choose, and we'll go in here and see this right now. If you go to main, okay, go to main, the agents are placed in main, the agents are cells, and we scroll down in main, and you'll notice that there's something called a more neighborhood applied, okay? That means we have 8 neighbors being considered. So if we consider a given cell, what are those 8 neighbors? So here's our cells, and ladies and gentlemen, here's our index cells. So that if we consider the update of this cells, what are the cells on which it depends? What are the 8? Yeah, just these cells around it. You'll notice that you can also pick out what's called the Euclidean one, where it depends only on 4 neighbors. And why don't we examine the consequences for that? Okay, we'll go and examine the consequences if we have that. I've changed the rule back to its original formulation. So how do you think this will change things? If it depends only on the 4 around it, north, south, east, west, not northeast, north. It's not very lively, ain't it? It's not too encouraging in terms of the survival. It disappears pretty quickly. We are counting up a lot fewer neighbors as counting as neighbors, and so it tends to be much more lonely as a cell and therefore be more likely to die out. Okay, so we can change the topology. Who's connected as being nearby whom, and in this case, 8 neighbors is pretty important. Okay, so I'm going to skip over some details, but the thing that I want to emphasize here is again, we have here a 2 models of time. What we've been dealing with for this model is what I call synchronous time or discrete time. All the agents change in lockstep. They all update together at fixed time points, discrete time points. There's no between time 1 and 2. There's only time 1, time 2, time 3. Okay? The idea here is when you have that sort of situation, you need to figure out what's going to be updated in this time, at this time, based on the values up to this time and not considering any other updates. So I noted that there's this separation of collecting the data needed to perform the update based on the current state, so that all that information is in hand before we update anything. Because once we start updating things, once we start actually updating whether or not a cell is alive, that's what this is setting, whether or not it's alive, or setting it here. When we're updating that, we don't want it to be affected by other cells that have updated in the same time step. So all the information that they need to figure out are they going to be alive in the next time step is it's actually calculated before anyone updates. And then they're all updated conceptually together, all at once. Okay? And we noted that that has a fair degree of parallelism associated with it. In principle, you could compute it in parallel across a large array or what have you. This is a type of computation that you'll see in a lot of agent-based models, which don't adhere to a continuous time frame. They do it in ticks. Part of the challenges of this is that if multiple things can occur in a given time step, then sometimes you have to broker which of them occurred first, and it can become quite a pain. In continuous time, we've dealt with this for most of our work, with system dynamics, and we dealt with this for agent-based modeling. Here, time runs as finely as needed by the modeler. In system dynamics, there's one time step imposed. You set a time step for the whole model. In agent-based modeling, time is handled as quickly as things happen in the model. It can be handled. So if certain processes occur really quickly, they can be handled at a very fine time step, very fine time scale. If other things happen only infrequently, they can be handled less frequently. Okay, and in this mode, this continuous time, often two agents are updating at somewhat different times, so they don't really have to worry about seeing which updates first. Okay, that's most of the cases that we've dealt with. If you have an agent that's going to transition according to a rate transition, and another agent that's going to transition according to, let's say, a rate transition, it's extremely unlikely they'll go off at the same time. So there's not a lot of worry about which goes off first. This might go off at time, 5.0, and this one at time 5.002, and they're not updating in lockstep, so there's no issue of them, needing to be brokered who got updated first. Okay. So I noted that in any logic, you can set whether you're going to use steps or not. So you'll notice here that that in this case we've actually updated the steps. So we're updating using handlers for the steps that are explicitly being handled here. And in general, if you go to a classes page, you can go and enable steps to be handled for that class. You can, and I think it's down here, and I'd have to find it exactly. There's a checkbox that will indicate do we handle time steps for this agent, and you have to check that in order for these steps to be enabled for an agent. So that's discrete time steps, and you can specify the step size that you want to use. Okay. Okay, I'll find it for you if you're interested. Let's go here. It's not going to be in these, I'm pretty sure. I will go. It used to be in the general of the agent, but it looks like they moved it. So is it in the model as a whole? No. Okay. Is it in main or in the population of agents? There it is. Main. If you go to main and you go to space and network, you'll see enable steps. Do you see that? So in main, under the space and network area, it'll say enable steps. In contrast, I'm going to check here, space and networks. Yeah, there's no option to enable steps because there's no embedded agent. So when you do it in main, it's enabling the steps for the agents within it. And which agents live in main? Well, these ones here are called cells. these cells. Okay, that's how you enable steps. Okay.
How will that affect like rates and that kind of stuff?
It's a great question. So what's going to go on, and we're going to have a lecture about this later, where this is talked about, but what's going on beneath the surface here in AnyLogic is that there's, and this is common for many packages, it's not specific about AnyLogic, there's a notion of what's called a schedule. And to be more specific, it's an event schedule. Okay? Now, when an agent comes into a state, it actually evaluates rate transitions and picks a time when that agent will leave via a given transition if it hasn't left earlier. Okay? So maybe when it comes into this state at the initial time, it'll pick it's going to leave at time 5. Okay? And meanwhile, there may be steps that are planned that are firing off at certain defined times here. Okay? Certain fixed times. There may be other agents who pick a different time for them to leave, and there may be timeouts that occur at different times. There, moreover, are things like sending another agent a message right now, which adds an event to be handled right now. So basically what's going on when AnyLogic is running behind the scenes is it's adding in these events, and it's jumping from event to the next event in order to handle that next event.
Okay.
So whatever event is up, it's going to go to that, advance time to that, and handle it. Okay. Now, in many models, the number of events is very large. And in fact, to see this clearly, I would invite you to go to AnyLogic help, because it's an important point. It's an interesting thing to see. If you go to AnyLogic help here, and actually what I really want to do is AnyLogic example models. I'm sorry, not help. Here we go. Here's example models, and I'm going to make it full screen by double clicking here. I don't know why it's, hey, man, okay. There we go. And now if we go down here, we will see there's something called, actually it's in how-to models here on the, oh, you know what, it's, I was going to show you one where it involves more events, but the problem is it can't run in the educational version. So what should I do? This is the personal learning version. Let's take one of the models we already have loaded. So there's a continuous time game of life rectangles that I asked you to load in last time. Okay. Let's go run that one, and we can ask it to show us some information. So I'm going to right-click on Emergent Patterns 2. There's another model which shows it particularly clearly, but because it's not going to be accessible to the version in the room. Here we go. Now, you'll notice down at the bottom there's certain information shown, but I can go up here and I can ask it, for example, to go display some additional information at the top. Now, down at the bottom, there's actually some additional things I can ask. For example, events per second. And events per second shows how many events on this schedule it's evaluating per second. Okay? There are some more advanced things called dynamic events, which you can create an event that will go off at a certain amount of time with information you tell it now. It'll go off later with that information. And those can be scheduled in here. Messages are scheduled in here. Time steps are scheduled in here. Transitions between states. And that's what this is all about in terms of the number of events per second. And in general, AnyLogic engine is running atop this quite sophisticated event handling mechanism where it's scheduling these events. Notably, some of these events actually get descheduled. Why would an event get descheduled? Why would you deschedule an event? Suppose you schedule this event to leave this state at a certain time. Why would it be descheduled? Anyone? Yeah.
Because before it was executed, the state that the transition depended on changed.
Yeah, so maybe there's, great, Rowan. So maybe there's a message transition from this state to a different state. And before this agent left this transition, it actually received a message. This is a message transition here. And so it went down to this other state. Boom, took it out. This event is no longer relevant, and so that event gets descheduled. What's another reason an event might get descheduled? The agent might die. The agent might disappear. Boom. It vamooshes. It's killed off, in which case all the events associated with it disappear as well. So events get descheduled, ladies and gentlemen. So any logic is running an event handler here, which handles and brokers these events and deschedules them behind the scenes to allow these models to run. Notably on this is what's called discrete event handling. So this is discrete event handling. And what's notable here is that events can occur as finely as needed. So if there's something which occurs here that's, requires a lot of action, events can get scheduled in very, very finely in time. A lot of things can occur very, very quickly. Maybe there's a crash that occurs in the stock market, and lots of things have to be simulated really quickly going on during that time. Or maybe there's a sudden change associated with a population, and you have to schedule a burst of activities. And then this is more like a period of stasis, where there's long periods between where events occur, comparatively speaking. This is something that's very hard to do in system dynamics modeling, where there's fixed time steps, but you can do in discrete event modeling, discrete event handling. You can schedule things as finely as you want. And a state chart that has a lot of action on a very fine time scale might become active. So ladies and gentlemen, here you'll see it processing events over time. And interestingly, they're creeping up. I guess it's a mark of becoming more structured. Okay, so a little bit about event handling. Did that help address your question? Yeah, Jordan? Yeah. Great. Okay, so ladies and gentlemen, let's talk. I'll post these slides that sort of describe this, but I'd like to talk a little bit about the spatial embedding here, because that's central to one of the reasons for showing this. Why would we have spatial context represented? Well, sometimes it expresses a central dynamic. So there's, only neighboring cell. A cell is influenced only by neighboring cells. There's no spooky action at a distance. Or there's transmission, for example, only through proximate contact. And we want to capture that. It's not transmission through the environment. It's not like, I catch norovirus through an environment that has fecal matter around. It's more point-to-point sort of contact. Secondly, it may provide you insight into certain phenomena, that there's certain spatial concentration. Percolation. This was something that was a notable feature of the models that you built last time for your problem set. When I say percolation, what do I mean? What do I mean? For a infection, or a rumor, for that matter, to spread across a network, we say it percolates across the network. Why do we say it percolates? What has to happen here?
Would be the delay it takes to cross the network.
Okay, there's a delay associated with it, but there's also a need for it to cross several bridges. It needs often to cross from different areas of the network. And if these are severed for some reason, for example, there's someone on the way that can't be infected or can't pass or won't pass on this rumor, then that transmission across the network is blocked. And this is a big phenomenon. This is not a small thing. It's a big phenomenon for a lot of network contexts where the random mixing assumption that we have in aggregate model that you can transmit to anyone is flawed. You fundamentally, a lot of what goes on in limiting the transmission is the fact that it can be blocked. And I would think that in the last problem of your last problem set, you saw that. You probably saw that with the agent-based model version of your infection transmission model, you were getting less spread of infection than you expected through the aggregate version. Why is that? Well, in the aggregate version, a person can affect anyone in the population. In the agent-based version, they can affect nearby people. But in order to reach someone way across the network, it's got to get over across the network. And if the network is blocked, if it's severed, if there's someone in the way who's already been recovered, if there's not a connection to that other person, there's no way from here to there, then it won't be transmitting. And much of what occurs, in fact, in transmission contexts that occur for childhood diseases is you need to have a buildup not only of a certain fraction of susceptibles. Do you remember with the aggregate modeling case? We saw this key role of fraction of susceptibles. Do you remember that? You know, if I'm an infective, how many people around me are susceptible? And if too many people around me are no longer susceptible, I'm not very effective at transmitting the infection. That much was true, and that pointed to an essential truth. But the fact is, what we didn't capture in the aggregate model was just the local nature of that transmission. We were assuming that we could transmit to anyone in the population. If we can only transmit to local people, it's very easy for it to be blocked in the way to other areas of the network. And really what has to happen is you not only build up people that need to be susceptible, but you need those bridges that have to be susceptible to reach other areas of the network. Okay? It has to get across, be able to cross that network to other individuals, and that requires individuals along the way needing to be in the right states, not just a certain fraction of the whole population being susceptible. Does that make sense? Okay, so this is an important feature, percolation. Sometimes, ladies and gentlemen, we want to explain patterns we see in the world that are spatial. We want to be able to explain why we see an expanding ring or what have you. Sometimes you want to reason about access to resources. If an individual is here, what resources do they have access to? Do they have access to certain grocery stores or supermarkets? If you're a deer, certain haystacks or grain bins or what have you. Based on where you are, there may be constraints on movement, like certain roads you can go across. You think about Saskatoon, right? There's certain bridges we can take across the river. And if you want to think about, movement patterns and things that depend on them, like traffic jams, you need to consider that connectivity, those constraints in the movement. If you want to compare spatial patterns against other patterns seen empirical observations, really this is about spatial reference modes. Spatial embedding is very desirable. Okay, let's continue on though to look at a different stylized model, one that abstracts away from cases but has been extremely influential. So I'd like you to go to example models, and I'd like you to pick out a model there. Okay, once again, we're in this kind of funky context. Okay, here we go. There's a model there called Schelling segregation. Okay, Schelling segregation. Now this is once again, what I consider a not an inelegant representation of it. I've provided you through the website a more elegant representation that we'll be turning to in a minute. But its elegance allowed it to, led to it to put aside one or two features of the situation. Okay, so here, ladies and gentlemen, is the situation, and we're going to run it up front. So this is a model. It was built by sociologist Thomas Schelling in the 1970s. And he was interested in the emergence of segregation in neighborhoods in the US. So the United States, like unfortunately many Canadian cities, has had historical problems with segregation. And if you look at city after city, Detroit, Los Angeles, Chicago, and Baltimore, there are big areas where there's one sort of people. Maybe it's wealthy people, maybe it's whites live in one area, and then other people, maybe it's lower income people, people who are of a different color who live in a different area. And he was very interested in this phenomenon. And one of the questions he was asking is, to what degree do we have to have recourse to very complex theories about this? To what degree could this be explained as a confluence of some simple processes? For example, small preferences on the part of individuals. So he built a little simulation to perform this. He wanted to see if we had a very simple rule where we had people arranged in patches, and a given individual would remain in their patch as long as they were comfortable with their environment. But once a certain fraction of those around them were different from them in appearance, they would consider moving. Okay? Very simple rule. It didn't posit real estate agents steering people based on their ethnic background. It didn't posit predatory banking loaning policies that did not favor people of color. It didn't posit outright discrimination that might prevent someone from moving into a neighborhood. Rather, it had a very simple idea. If the people around you are not sufficiently similar to you, you might want to move. What would the result be of that simple rule applied at an individual level? So in order to simulate this, Thomas Schelling used a checkers board. And he had pennies, US pennies. And they were heads up or heads down. I think it's Abraham Lincoln on the penny. And so if it was heads up, it would be considered a white neighborhood. Heads down, it would be considered a black neighborhood. Something along those lines. Or red and black without reference to particular ethnic groups. And he simulated these rules on that checkerboard. And I think he did it on an airplane flight, if I'm not mistaken. I don't know how he got the checkerboard on there. Ladies and gentlemen, these days we don't need our checkerboard, so let's go run the model. So here we have a situation where we have empty spaces shown in white, where we have two types of individuals, red and black. Okay? And up here on the top is an indication of people's degree of preference for people like them. What this is going to mean is that if less than this if they are surrounded by people who constitute less than this fraction like them, in other words, if fewer than 68% of the people around them are of the same color, they'll move with a certain probability. And this again is a discrete time step. And what you see emerging is something that's kind of striking. The initial model, if we go back and we restart it again, you'll notice that the initial model has people in totally random selection. It's just that if you run it out, and I'll go and do a time scale here. If you run it out, what you'll see is even with 50% preferences, that I'll tend to move if fewer than 50% of the people are like me. In other words, if most people around me don't look like me, I'll have a certain chance of moving in this time step. You can get this emergence of quite significant patterns of segregation. We'll try that again. Maybe we'll start with a higher fraction, so that's 60%. Okay, we will go and restart it again, and here's 70%. What do you think if we started up with a very small level? One thing you can do is you can do this to step it, just to start it, and we're at step 0. And let's suppose we were to lower this very far. What would we see if we had only 10%? What do you think you'd see as a result? Anyone? Almost no movement. People don't need to move. They're comfortable with whoever's around them. If they're a red cell and next to them are 4 black cells, that's fine. So almost no movement. How if we move it up a little bit, say to to 20%. Let's say to 30%. What will we see then, do you think? Does it reach a stable point? Is there a fixed point here? Yeah? What does that mean if there's a fixed point? Everyone's happy. They've all gotten into a configuration where they're comfortable. And yes, there was some maybe movement around early on. You'll see if we were to stop that and we were to sort of advance to cell 1, we were to set this back to 40% here, and we were to run this flat out, there's some initial movement, but then people get into the state where it's kind of maximize the global happiness function. Okay? Now, as this goes up from 40% to 50%, what do you think is going to happen? So why are we seeing these patches? What's going on? These patches are emergent phenomenon. We didn't build them into the model. But why did they come about? Why is there a patch of black here and patch of red? Yeah, it's achieved a sort of equilibrium. People are seeking most people around them to be like them, and so they're moving until they can get that sort of environment where it will be similar. And you notice as we move it up, it's actually getting larger patches, 76%, 86. Okay, what's going on at between those points? Okay, here's 76. Okay, come on. Okay, it's trying to find an appropriate configuration. %. It looks entropic. What's going on here? You would think you'd get, what's that? They can't find a stable place. There's a lot of dissatisfied people trying to search for enclaves just like them. And they're not able to find it here. So that's in constant churn. It's constantly churning. Meanwhile, you'll see this pattern of emergence of these large patterns of homogeneity, with somewhat lower values. But at some point, it becomes untenable. You're never going to find a situation that provides that level of homogeneity. Now, let me ask this: if you were to change the fraction of white space, do you think that would change what would be stable?
Yeah.
And how would it change it?
Well, you can imagine if there was enough empty spaces, you could imagine having 100% affinity.
Yeah.
Simply having two sections.
Exactly.
Right down the middle.
Exactly. So, ladies and gentlemen, let's go to main, and here we go. Here we go to people, for example. And here, you'll notice that there's an initial number of agents of 8,000. That's not a very nice way to describe it from a software engineer perspective. Let's put in a parameter here, okay? This parameter will be population size, okay? What type will it be? And don't tell me it's a Boolean. What is it? An int. Thank you. Okay, so maybe by default we'll have 8,000. Okay, and here we go. We'll have an initial population not of hard-coded 8,000, but of population size. Right? Great. Okay. I'm forewarned. And forearmed is forearmed. Okay. Great. There we go. Okay, so having done that, I'd like you to go now create an alternative scenario where we have a population of 2,000, let's say. So we'll do Schelling segregation, new, experiment, and we'll say population 2,000. Okay? So instead of being 8,000, we'll instead do it 2,000. Okay? What do you think to what will that lead? Rowan prognosticated? Okay, I would argue this is a stable configuration. Why?
There's enough white space to buffer them
Yeah,
from each other.
exactly. Even at 90%, they're isolated from each other. They've sort of self-isolated. By contrast, if we were to bump this up to, let's make a copy of it. Well, or we can just do a new one. And we could make it 5,000 here. As this initial population rises, what do you think we'd see now for 5,000? Do you think they'll be able to isolate as easily? Okay. Okay, now we're upping the ante. Okay, there still looks to be a threshold where they're not going to be able to find a comfortable match. Okay, so 77%, you could see, there's some sort of separation between these groups going on. It's not just that they're clustered away from each other. They're like putting space between each other so they don't have to be near each other, right? But beyond a certain point, we still have this entropic situation. Ladies and gentlemen, Schelling segregation model, quite influential in terms of its thinking. This doesn't simulate Detroit. This doesn't simulate New York. This doesn't simulate LA. But it helps understand something about how individual preferences, even fairly modest ones, such as wanting to live with a situation where, about half the people near you are similar, you can get big patterns of discrimination. This doesn't require to explain it. These patterns don't require, huge preferences. Modest preferences added up person after person after person can explain these big patterns in this case. Now, the key element that this had, so this is a discrete space. This, ladies and gentlemen, is a discrete time model. Time updates in lockstep. So if you go to person and you go look at it, you will find that there's on before step and on step. I'm going to go open up a model that I posted to the site. You don't have to do this. This is more sort of a one that I did ask you to download last time in anticipation of this, but I'm not going to spend that much time on it. So this one is going to be a model that's also based on the Schelling segregation, but it's going to be a little bit different in terms of its particulars. Okay, so it's called continuous time Schelling segregation with free cell list. Okay, this is a model that I built for some folks at UCLA who are from sociology there and who are interested in some of these effects. And within this context, we generalize the Schelling segregation model to have more than two groups. So you could have n groups, each with their own color, and each with a sort of type of preference. And you'll notice, okay, that's an unfortunate visualization. I thought we had cleaned that up, but I will go move this from main and move it over. There we go, over to the side, and here we go. Here it takes into account a certain radius, not just your immediate neighbors, but those who live within a certain distance of each other. And it further takes into account the aspects of the of multiple populations, and it tends to run slower, but you tend to have these sort of patchwork communities here. A notable feature of this, if you go look at person, is that this model actually had in place a continuous time representation where they consider a move with a certain period, and basically they're basically rating their current cell versus best rating of other cells, and they try to find others that are more favorable, and if they found them, they move to them. They jump to them. So there's this key jump to cell here. So discrete space, discrete. This is continuous time. The other one was discrete time. What's the difference between this and Conway's Game of Life? What's an important difference between these? Spatial environment. What's an important difference? Movement. Cells move. They don't just die or get colonized. They actually move, and they retain things as they move. Okay, so ladies and gentlemen, these are fun to play around with further, but our interests here are extending to other areas of movement that can help you in your work for your problem set. So I'd like you to now go and call up I think in the interest of time, we'll do one that's a little bit of a fun one. It can be done in about 30 minutes, and we will go perform this right now. So I am going to close these off, and we're going to create a new model. Do I want to save these? No. Boom. Okay, so ladies and gentlemen, we're going to create a model that exhibits continuous movement in continuous space. Not in the discrete patches, but in continuous space. How do we do that? Okay, so clear your slate. We're going to create a new model, and this model is going to be called ABM Mouse Mobility. Okay? And the time units of this are going to be in minutes. Okay? Here we go. ABM Mouse Mobility. And I'm going to call it CMVT 394 Fall 2016. You don't have to do that. Okay. Ladies and gentlemen, I'd like you now to go and to create a person. Okay, here's an agent, and this is going to be a person, and we are going to give this person a representation here with down here with this sort of humanoid shape down here in the palettes under pictures. Okay, and we are going to go to main, and we are going to create a population of people. How do we do that? Speak as in a Greek chorus. Okay, well, the Greeks would be ashamed. Okay, make population. Come on, you drag them in. You know that as well as I do. I hope you do, or else we've got a thing coming on the problem sets. Okay, and then go to agent, and I'd like you to drag in a parameter that's going to be population size. Population size, and its type is going to be speak, int. Okay, and it's of size 100. Boom. Make it a population of now initial number of agents given by population size. Okay. Now, we're going to give a random layout to these individuals. And I'm going to show you a way that's more robust. We've used it before, and it's my preference. So ladies and gentlemen, I'd like you to go to main, go to the population, and place the agents in the specified points. And it's going to be, we're going to place them in an X location between uniformly drawn from a continuous uniform distribution between 0 and this dot space width. You've done this before. And the next one will be uniform between 0 and what? This dot space height. Thank you. Okay, good. Okay, build your model. Make sure it's a happy camper. Okay. Okay. Let's run it and just see what happens. What will we see when we run this model?
Just some agents spread around.
Yeah, there'll be agents spread around. Great. Okay. Okay. Soon enough, they'll be more lively. Trust me. Okay. Next, I would like you to go to Palette here, and I would like you to go down to the presentation area of Palette, and I would like you to go add in a rectangle whose upper left is going to be at the origin, and it's of width, and you can set this in its properties. Width and height 500. Okay? Okay, ladies and gentlemen. Now, what I'd like you to do, having added that rectangle, we've just added it, the upper left-hand corner, and we have made it width and height 500. Whence did that rectangle come, ladies and gentlemen? From the presentation palette. And now we will bend it to our will. Okay? So now click on the rectangle and go to the properties of the rectangle. And I would like to invite you to enter into the esteemed area of the advanced section. Okay? Actually, it doesn't require a huge amount of advanced knowledge, but go to on-click. And on-click, what I'd like you to do here, okay, I'm sorry. Yes. For each person, ladies and gentlemen, within the population, for person P in the population, I'd like to do P dot move to, and you'll notice that this little rectangle tells us click X and click Y are the locations relative to the origin of the shape. So I'm going to say click X, comma, click Y. Click Y. Okay? Now, let's run this. Let's run this. There's a more beautiful way we could do that. And I'm sorely tempted to show you, but we got to get out of here soon. Okay, so ladies and gentlemen, you notice what's the problem here? The rectangle's on top. So let's go back to the rectangle. And what we need to do is we need to go to the appearances area of the actually, we need to right-click on it and do order send to back. So right-click on the rectangle, do order send to back. Okay? So now it'll be behind the agents. Okay. Okay, here we go. There we go. What just happened? Okay? Okay. Okay, so let's try that again. Okay, here we go. So I'm going to run it. And I'm going to slow down time so you can see. And okay. Okay, so what just happened, ladies and gentlemen? Yeah, we moved them all there. That's what happened when we clicked on that, right? So that's a start. We're going to have some more fun. First of all, I'm going to color the rectangle yellow for a bit of color, and since it's behind all the agents, it is what might be called Huang Ho. Okay, so here let's add a state chart into person, Okay, we're going to go to palette, and we're going to go to the state here, state chart palette, and we're going to go add in here a mobility state chart. Okay, mobility state chart. And there's going to be a single state here, which is going to be called in motion. Okay, as I am wont, I capitalize it. Okay, and here, ladies and gentlemen, we are going to take a transition, and we are going to bend it to our will by double-clicking in the middle and bending it back. Now, this transition will be called arrival. It'll indicate when they've arrived at their state. Okay? And the transition type will be agent arrival. Do you see that? Agent arrival transition? See or not? Okay. Okay. There we go. Great. Okay, ladies and gentlemen. Next, in motion, we are going to set this agent into motion. Okay? And we're going to set it into motion with around the certain point. We're going to have it undergo what's called a random walk. Anyone know what a random walk is here? What?
Like a graph?
Okay, you could perform a random walk on a graph. What would that involve?
Like going from one node to another randomly.
That's right. You pick a random node to go to. Here, it's going to involve picking a random point around the agent and heading to that point. Okay? So here we're going to do, when they enter this in-motion state, whether from the start or whether having arrived and re-entering, we're going to do this dot move to. When did we use move to before? Not 10 minutes thence. When did we use this before?
On the click action.
Yeah, on the click action. So that will send the agent to a certain location, and it automatically updates over time according to its progress. And when it arrives, guess what can be triggered? The mouse suggests it, ladies and gentlemen. Arrival action. Okay, so we're going to move this agent to a position, and that position we're going to specify to move to. It needs two things. It needs an X and a Y. Okay? That's one of the things that you can give it. So we are going to draw its new location. Its new location, X, is going to be drawn from right around its current point. Now, its current point, ladies and gentlemen, is this dot get X, my current X location. And we're going to draw a value from a normal distribution whose mean is this, whose average value is that. It's going to be a normal distribution around the current X point. So if this is its X location here, we're going to draw from a normal distribution in the X direction with a standard deviation sigma equals 20. Okay, now, within a normal software package, one would expect the normal distribution to specify the mean first and then the standard deviation. But any logic is a software package extraordinary in many respects, and this is one of them. That's not a very nice one. So you actually have to specify the standard deviation first. It's one of the more surprising things you learn. So, ladies and gentlemen, here's the normal distribution. You'll notice sigma becomes before the mu. Standard deviation and then the mean. So, what is this saying? Can anyone interpret this? So what are we doing? We're drawing from a normal distribution whose mean is what? No, its mean is actually the X value, and its standard deviation is this. So it's around their current X value. And we will do the same, mutatis mutandis, with the Y value. So what does this have to be changed to? Okay, get Y. Good. Okay. I appreciate the Greek chorus. Okay, ladies and gentlemen, Now let's be sure that it's a happy camper and the parentheses match and various good things. Okay, so now let's run this. What do you think will happen?
There will be a cluster and then a couple like stragglers on the outside.
Okay. So the suggestion is one of entropy. Okay, they're moving around. What happens if we click? Okay. Okay. Well, I told you it'll be getting more lively. Okay. So what happens is we run this thing over time. Suppose we were to go up here and we would do the view so we can zoom out. So what do you think will happen as we run it over time?
They'll just kind of randomly spread out.
Okay, they're kind of spreading out. We click. Okay, they're kind of coalescing, right? Okay. And then they're moving out. This is what's called random motion, Brownian motion. Brownian motion involves this kind of random motion in arbitrary directions. Okay, so that's good, ladies and gentlemen. Now, I think time is short here. I'm wondering if we have time for one more thing here. But I want to draw attention to a couple essential features of this situation. One is that these individuals are operating in continuous time. So this arrival is triggered at what point? At what point is this arrival triggered?
When they reach their destination.
When they reach their destination, be it the point we clicked on which they converge, or be it the destination to which they moved. When they reach that destination, this occurs. How long it takes them to get to that destination will be a function of where that destination was compared to their original location and their speed, right? And their speed. So, ladies and gentlemen, I'd like you to reflect on that fundamentally the timing here is in continuous time. More than that, we have continuous space. So their movement in space is continuous. They're moving not in discrete patches, but they're moving sort of smoothly through space. So the smoothness of it may not seem obvious when viewed at a distance. If you actually slow it down to a more stately pace, you'll see that they move. And perhaps the biggest demonstration of it would be as I do this, in which they coalesce in the center. You could see the smoothness of their trajectories. So once again, now we have movement, mobility in continuous time and continuous space. And actually, as a feature of that person, there's an indication of their of the speed with which they move, their initial speed in meters per second. And indeed, if you scroll up, any logic has a mapping. I think we've mentioned it before, between space, spatial distances versus visual distances. We won't go into this, but I'd like you to add one more feature to this model, if you may. It's a model of some interest already, but I would like to, ladies and gentlemen, go and take this transition out, bend it to our will again, and now I'd like to drag in from the palette a branch. Okay? A branch, ladies and gentlemen. Now, what does the branch represent? Can anyone tell me?
Decision about what state.
Yeah, it's a decision. And sometimes we use branches when we first are coming into a state chart to figure out on what state we initially go. Do we start in this state or that state? Here, we're going to have a transition here, okay? And we're going to have a default branch, ladies and gentlemen, back to in motion, okay? Here we go. A default branch. You notice it's dotted, which indicates it's the default branch. And the action associated with the default branch, ladies and gentlemen, will be we're going to move the move out of this, the code from in motion, and we're going to put it in two places. One, we're going to put it in the entry point. So we're going to put it where we enter this. So when they first go, they're going to move to a random point around their current location. Secondly, we're going to put it on this default transition. So this is, random movement is that default transition. Okay, next. Now, ladies and gentlemen, the plot thickens. Okay? So we're going to add a parameter to main. We're going to add a parameter from the agent, and this is going to be called probability of friend seeking movement. Okay? There's probably a nice Latin phrase for that, but I'm innocent of it right now. Okay, so it's going to be a Boolean. Oh, sorry, it's going to be a double. Excuse me, it's a probability. It's going to be 0.1. Okay. And next, we're going to go back to person. So I added probability of friend seeking movement, default value 0.1. Next here, and the time is a ticking. I'm aware of that. So ladies and gentlemen, the default action is taken as a default if no other ones occur. So in order to describe other transitions, we can drag in a transition from either the state chart palette or the agent palette into in motion. And it's going to look a little bit messy, but what it lacks in aesthetics, it will make up for in utility. So I'd like this to be called friend seeking. Do you see whither I go? It's less than a resounding answer, but basically, I'm adding social interaction. I'm adding inter-agent interactions. Thus far, the agents have been solitudes, moving around in a Brownian motion that's atomistic. Now, ladies and gentlemen, we want to add in this element of random movement. Okay, so it's not filling this in. I think it was probability of friend seeking movement, and that will be, sorry, what am I doing? I stand before you confuse it. Okay, this should be random true of probability of friend seeking movement. Okay, great. Excellent, ladies and gentlemen. We are nearing completion of this exercise, and this is what I'd like you to do. For this action, I'd like you to do the following. This dot move to, this dot get nearest agent, main dot population. So in other words, I want to ask of all the agents in the population, which is the nearest one? And once I have that agent selected, what do I do to it? Or what do I do to myself? I get myself to move towards that agent. Okay? Okay, ladies and gentlemen, next, in the final moments, we added in this parameter. Now we will add a slider. A slider, no less, ladies and gentlemen, from controls palette. We'll add in a slider. Whence did I get that? From the controls palette here beneath analysis. Here's a slider. This slider will be, friend seeking probability slider. Okay, I could have called it something shorter to good effect. And I'll make it a little bit smaller. It will be linked to probability of friend seeking movement. I clicked link to, and I chose probability of friend seeking movement. Its minimum value be 0, and its maximum, ladies and gentlemen, 1.0. After all, it's linked to this probability. Okay? Ladies and gentlemen, let's run this thing. Okay? Okay, so ladies and gentlemen, here we have an atomistic movement here, fairly atomistic. I'm going to go and I'm going to do view and zoom out a little bit. Is it quite the Brownian motion we saw before? Let's sort of up this slider, ladies and gentlemen. As we up the slider, oh, what am I doing? So we up the slider. What are we seeing? Okay, how if we lower the slider? What are we seeing now?
Just random.
It's sort of fairly atomistic, yes. Though it's hard to tell with the sort of update speed how many pairs there are. Let's bring all the slider up. Okay, now what do we have? Yeah, there's kind of these groups forming, right? And the groups are moving around randomly. You notice that they're only bound to the nearest one. They have kind of a bat-like appearance by my crude aesthetics. I don't know if they're, I guess we could ask Vikram Misra. He might be able to comment. But ladies and gentlemen, they're not quite attracted. Why aren't these two, or these ones, attracted to each other? Why do we see this kind of dyadic feature?
It's only the first.
You're only finding the nearest one. There's no social force. It's not, I'm being pulled towards the set of them near me. It's only, I'm going towards the nearest one. So we tend to have this kind of budding up effect. But you'll notice neither is it quite as random as before, because they're often sort of resyncing with each other, canceling each other's movements out, right? And you don't get quite as fast a sort of diffusion away as we did previously. You have it sort of more staying in place. Okay. Anyway, continuous movement. This will be useful for your problem set, ladies and gentlemen. And it will be useful for actually several problems that we'll be seeing on the problem set. We'll be seeing also some flocking behavior in CMPT 470 that's related to this. That's a lot of fun. Okay? So if you want, you could challenge yourself to create a little flocking model where you're not only considering the characteristics of the nearest agent, but of a whole set of agents nearby you and shaping your movements. So that's all for today. Thank you very much. And I will go and post this. I've lost some previous recordings, so I'm taking effort